In this video, I want to talk about Newton's 3 laws of motion. So the first law is the law of inertia. And the key idea is that objects like to maintain their current velocity. For example, let's say this ball is not moving, so therefore it has a velocity of 0 meters per second. This ball wants to maintain this velocity of 0 meters per second. And we can wait 1 second later, 5 seconds later, 1 day later. We know this ball will still be moving with no velocity at 0 meters per second because this ball wants to maintain this current velocity of 0 meters per second. So because this object wants to maintain its current velocity of 0 meters per second, the only way to change this velocity is to apply an external force. So if we were to apply an external force, then we could change this velocity. Now maybe the ball would be moving at a velocity of 5 meters per second. So again, the key idea when it comes to the law of inertia is that objects have a tendency to want to maintain their current velocities. And something else important to realize is the more mass an object has, the more inertia the object has, and therefore the more it wants to maintain its current velocity. So we can see both of these objects have mass. This is 10 kilogram mass ball and this is a 1 kilogram mass ball. So because they both have mass, they both have inertia. So they want to maintain their current velocities. However, because this ball has more mass, therefore it has more inertia. So therefore it has a higher tendency to want to maintain its current velocity, which essentially means it's harder to move. It wants to maintain its current velocity of 0 meters per second. So because it has so much mass, it wants to maintain this current velocity, so it's hard to move. And that's intuitive. If you have a heavy ball and a light ball, it makes sense that it's harder to move this heavy ball. Why? Because it has more mass, so therefore it has more inertia, so it wants to maintain this current velocity. So now let's try a thought experiment. Let's imagine we have this large 10 kilogram mass ball, and let's imagine we have this small 1 kilogram mass ball. What would happen if we apply 10 Newton forces on both of these objects? Well, if we apply 10 Newton force on this large ball, we would imagine a very small increase in velocity. And that makes sense because it's such a large ball. If we were to apply 10 Newton force, it would barely move this ball. So it would barely increase the velocity. However, what would happen if we applied a 10 Newton force on this small 1 kilogram ball? Well, if we apply a 10 Newton force, this ball is going to go flying. Because it's such a small ball, this ball is going to go flying. So it's going to have a very large increase in velocity. So again, this is because of inertia. Because this ball has so much mass, therefore this ball has a lot of inertia, so it wants to maintain its current velocity. So therefore applying this 10 Newton force will cause a very small increase in velocity because again, it's resisting a change in velocity. It wants to maintain its current velocity. So applying a 10 Newton force will cause a very small increase in velocity. But because this ball has so little mass, it has very little inertia. So therefore applying a 10 Newton force will allow this ball to go flying and will cause a sharp increase in its velocity. So let's think about another example. Let's say we have this wrench flying in outer space with a current velocity of 5 meters per second. Well, again, this wrench has mass. So because it has mass, it has inertia. And because it has inertia, we know it wants to maintain its current velocity. So therefore, if this wrench is flying at 5 meters per second, it's going to maintain this velocity of 5 meters per second indefinitely. And you've probably seen in movies and in cartoons when something is flying in outer space, it continues to fly in outer space with a constant velocity. Why is that true? Well, again, this object has mass, so therefore it wants to maintain its current velocity. So it's going to maintain this velocity of 5 meters per second indefinitely. And it's going to maintain this velocity, and the only way to change this velocity is to apply an external force. So let's imagine another example. Let's say we have this car traveling at 50 meters per second. And let's say we have these books on top of this car. Well, if this car is traveling at 50 meters per second, we know these books are going to travel at 50 meters per second because these books are on the car. However, what's going to happen if this car runs into this brick wall? Well, if this car hits this brick wall, we know the car is going to instantly stop. We're going to cause a change in the velocity because this brick wall applies a force, causing this to stop moving and having a velocity of 0 meters per second. But what's going to happen to these books? Well, you can probably intuitively imagine if this car were to run into this wall, these books would go flying off. Why would these books go flying off? Well, again, remember, initially these books were traveling at 50 meters per second. And again, remember, these books have mass, so therefore they have inertia, so they want to maintain this velocity of 50 meters per second. So therefore, when this car hits this brick wall, these books have inertia, so therefore they're going to want to maintain this velocity of 50 meters per second, so that's why they're going to fly off with the velocity of 50 meters per second. They have inertia, so they want to maintain this current velocity of 50 meters per second. So again, this is Newton's first law, the law of inertia. And the key idea is whenever an object has mass, it has inertia. And whenever an object has inertia, that means it wants to maintain its current velocity, whatever that velocity is. And again, the more mass an object has, the more inertia the object has, and the more it wants to maintain its current velocity, and the more it will resist a change in velocity. So therefore, the only way to change the velocity is to apply an external force. And we learned the larger the force, the larger the change in velocity. And that makes sense. The larger the force we apply, the larger the change in its velocity. But remember, what is a change in velocity? A change in velocity is simply an acceleration. We know the definition of acceleration is a change in velocity. So really what we're saying is the increased force an object feels, the increased acceleration the object will go through. So again, both of these are saying the same thing because again, acceleration means a change in velocity. So this brings us to Newton's second law. Newton's second law is that force equals mass times acceleration. So really, these are telling us the same thing. The larger the force, the larger the acceleration. The larger the force, the larger the acceleration. And again, an acceleration is simply a change in velocity. So Newton's second law is simply this equation that describes motion and describes how motion changes when you apply an external force. So let's try an example. Let's say we have this 10 kilogram mass ball, and let's say we have this 1 kilogram mass ball. What's going to happen if we apply 10 Newton force to both of these balls? How are their accelerations going to change? Well, again, to solve this, we simply use Newton's second law. So again, we would apply the force, and we would apply the mass, and we would solve for acceleration. And we would do the same thing with this ball. So if you plug in the numbers, you would get these equations. So now you could simply solve for acceleration. So if you were to solve for acceleration for both of these equations, for this ball, you would get an acceleration of 1 meters per second squared, and for this ball, you would get an acceleration of 10 meters per second squared. But according to what we learned earlier about inertia, this makes sense. It makes sense if we apply a 10 Newton force to this large ball, it's going to cause a very small acceleration, a very small increase in velocity. However, if we apply 10 Newton force to this very small ball, it's going to cause a large acceleration, a large increase in its velocity. Because again, this makes sense. This object has more mass, so it has more inertia, so it resists a change in velocity. So therefore, it'll have a small acceleration. So again, Newton's second law is simply this equation that describes how forces cause accelerations. And again, forces cause changes in velocity, aka accelerations. And we can see that these forces cause accelerations. Let's try another example. Let's say we have two 1 kilogram mass balls. However, let's say for one of the balls we apply 10 Newton force, and to the other ball we apply 1 Newton force. How will we expect these balls to accelerate? Well, again, we simply use Newton's second law, and we would plug in these variables into Newton's second law. So if we did that, we would get an acceleration for this ball of 10 meters per second squared, and for this ball, we would get 1 meter per second squared. And this makes sense, because again, keep in mind, both of these balls have the same mass, but if we apply larger force, you would expect a larger acceleration. And for this ball, if we were to apply a smaller force, we would expect a smaller acceleration. So again, this is logical and intuitive, so this makes sense. So again, Newton's second law tells us how forces cause accelerations. And again, the higher the force, the higher the acceleration. And that's what this is telling us. The higher the force, higher the acceleration. But now let's try a tricky example. Let's say we have two 1 kilogram mass balls, so they both have the same mass. But let's say this ball, we apply 15 Newton force in this direction and a 5 Newton force in this direction. And let's say this ball, we apply 10 Newton force in this direction. Well, something important to realize is physically, these are both the same thing. Because if this ball feels a 15 Newton force in this direction and a 5 Newton force in this direction, if you were to add up these forces, this ball would feel a net force of 10 newtons. So therefore, both of these balls are essentially feeling the exact same thing. This ball is feeling 10 newtons, and this ball is also feeling a net of 10 newtons. So now that we know this, how do we use these equations? Well, again, we know we would apply the mass and the force. But for this ball, how would we plug in these values? Would we apply 5 newtons or would we apply a 15 newtons? Well, what's important to realize is really the way this equation should be drawn is like this. In reality, the way you use Newton's second law is the net force equals the mass times acceleration. So therefore, what is the net force this object is feeling? The net force is 10 newtons, 15 newtons in this direction, 5 newtons in this direction. So the net force is 10 newtons. So you would plug in 10 newtons. And again, this ball is only feeling 10 newtons, so clearly the net force is 10 newtons. So again, if you were to plug in the net force to both of these equations and plug in the mass, you would solve an acceleration of 10 meters per second squared. So both of these balls would feel an acceleration of 10 meters per second squared. So the key point is when using Newton's second law, you're supposed to plug in the net force the object is feeling. So again, the net force this object is feeling is 10 newtons, so you would plug in 10 newtons. And you would see physically these balls are both experiencing the same force. So that's why they both have the same acceleration. And something important to realize is Newton's second law describes a real physical phenomenon. So whenever a 10 kilogram mass ball feels a 10 Newton force, it's going to acceleration at 1 meters per second squared, what Newton's second law tells us. So it doesn't matter if it's a red rubber ball, or if it's a donut, or if it's a beach ball. Whenever there's a 10 kilogram mass object feeling a 10 Newton force, it's going to accelerate at 1 meters per second squared. So it doesn't matter what object it is, as long as it's a 10 kilogram mass feeling a 10 Newton force, it's always going to accelerate at 1 meters per second squared. And another way you can look at this is whenever there's a 10 kilogram mass object accelerating at 1 meters per second squared, you know it has to be feeling 10 newtons. That's the only amount of force it could possibly be feeling. Because again, that's what Newton's second law tells us. 10 kilogram mass times 1 meters per second squared equals 10 newtons. So it doesn't matter if it's a donut or a beach ball, whenever there's a 10 kilogram mass feeling an acceleration of 1 meters per second squared, you know if this is happening, you know it has to be feeling a 10 Newton force. That's the only possible force it could be feeling whenever there's a 10 kilogram mass moving at this acceleration. So now I want to talk about Newton's third law. And Newton's third law is that every force has an equal and opposite force. But really the key idea is that you will never see one single isolated force in the universe. There is not one single example you can think of where you see only one single isolated force. That will never happen. Whenever there's a force, there's an equal and opposite force because forces come in pairs. You will never see one single force. So let's try an example. Let's say we have this beach ball, and let's say we slap this beach ball with the force of 10 newtons. What's going to happen? Well, if we slap this beach ball, we know this beach ball is going to feel a force of 10 newtons. So this ball is going to go flying off. However, if we slap this ball and apply 10 Newton force to this ball, we know every force has an equal and opposite force because forces come in pairs. So where is the equal and opposite force? Well, if you slap a ball, you're going to feel a force of 10 newtons. And you know this is true because if you close your eyes and if you slap a ball, you can feel it. You can feel that force. So clearly the ball feels a force because that's why it goes flying off. But you're also going to feel a force. So these are equal and opposite forces. They're equal in magnitude. They're both 10 newtons, but they're opposite in direction. This ball will go flying in this direction, and you'll feel a force going in the opposite direction, 180-degree opposite direction. So again, the key idea is that forces come in pairs. You will never see one single force. Whenever there's a force, there has to be an equal and opposite force. Equal in magnitude, opposite in direction. And forces come in pairs. So these are equal and opposite pair forces. But something really important to realize, and a mistake that people commonly make, is that a single object will never feel both equal and opposite forces. Whenever there are one of these pairs of equal and opposite forces, these forces will be felt by different objects. So this beach ball feels one of the equal and opposite forces, and the hand feels the other equal and opposite forces. So there will never be one object that feels both equal and opposite forces. And that makes sense because if this beach ball felt both equal and opposite forces, it wouldn't move. And there would be no motion in the universe. So again, the Newton's third law, the key idea is that you will never see one single isolated force. Forces come in pairs. And these forces that come in pairs are always equal in magnitude, opposite in direction. And these equal and opposite forces will never be felt by the same object. Different objects are going to feel these equal opposite pair forces. So let's try an example. Let's say we have this table with these books on top of it. We know these books are feeling a force due to gravity. And we know this because if we were to throw off these books, we know these books would go flying down because they're feeling a force of gravity. So again, this should be pretty intuitive. However, what is the equal and opposite force? Because again, we know due to Newton's third law, forces always come in pairs. You will never see one single isolated force. So what is the equal opposite force to this force of gravity that these books are feeling? Well, we know due to the law of gravity, if these books feel a force of gravity towards the Earth, we know the Earth is going to feel a force of gravity towards the books. So these are a pair of equal and opposite forces. Equal in magnitude, opposite in direction. These books feel a force downward, the Earth feels a force upward. And again, you could solve the magnitude of this force using this law of gravity, where again, this is the gravitational constant, this m represents the mass of these books, this m represents the mass of the Earth, and this r represents the distance between them. So if you were to plug in all those values, you would get a force of gravity. And that force of gravity is the force that these books feel towards the Earth, and that the force that the Earth feels towards the books. So these are a pair of equal and opposite forces. So let's try another example. So we know these books are feeling a force of gravity. So therefore it makes sense that these books are applying a force onto this table. So we could define this force that the books apply onto the table. The force that books apply onto table. And we know these books are applying a force onto the table. Because if you imagine holding onto these books, you would feel a force that these books apply onto the hand. The force that the books apply onto the hand. And we know this because if you were to close your eyes, you could feel these books. So clearly the books are applying a force onto the hand. So therefore, if these books were on this table, we know these books would apply force onto this table. So that's this force. So what's the equal and opposite force? Well, we know the table would apply force onto the books. So again, the force that the table applies onto the books. So these are a pair of equal and opposite forces. Equal equal in magnitude, opposite in direction. So again, these are a pair of equal and opposite forces. And there are a couple other examples. For example, this table is applying a force onto the earth, and the earth applies a force onto the table. And also we know this table feels a force of gravity towards the earth, and therefore the earth feels a force of gravity towards the table. So these are a couple pairs of equal and opposite forces. So again, Newton's third law states that all forces come in pairs. You will never see one single isolated force. And these forces are equal and opposite forces, equal in magnitude, opposite in direction. And also, these forces will never be felt by the same object. For example, if these books feel one force, then we know the equal and opposite force will be felt by another object, in this example by the earth. So this is Newton's third law. So again, these are Newton's 3 laws of motion, and these are really the basis of physics. So if you want to do well in physics and on the MCAT, you really need to understand these 3 laws.